Hi and welcome to this video where we're going to cover the Leaving Cert Higher Level Inferential Statistics exam questions. So we're going to focus in on all the different styles of questions that you can be asked. We won't be able to cover everything, but we'll cover the majority of subtopics within inferential statistics and we'll get a chance to see how these work. This video would be good to use in conjunction with the inferential statistics review and I'll have that linked in the description below. Example 6.1, Central Limit Theorem and Margin of Error. So it is known that data on farm sizes is not normally distributed. The Research Institute could take many large random samples of farm sites and create a sampling distribution of the means of all these samples. Give one reason why they might do this. Well, when we take enough samples, so when n is greater than or equal to 30, the distribution will act like a normal distribution. So we'll see that it starts to act normally. And this is called the central limit theorem. Normal distribution. And when we have something that is normally distributed, that makes our life so much easier because we're going to be able to then work with it in a way we can't otherwise. So that's the central limit theorem. So then the Research Institute carried out a survey into the use of agricultural land. N farmers were surveyed and the margin of error was 4.5. Find the value of n. So this is an important formula that's not in the log tables. So it's important that you know this formula. Okay, so we have margin of error. So this is one you need to know off by heart. Margin of error is equal to 1 over the square root of n. So your margin of error will be given in decimal. So we have 0.045 is equal to 1 over square root of n. I like to flip it, so use the reciprocal 0.045. That means n is equal to 1 over 0.045. And we square it, and when you do that, we're left with 493.827, and that would be 494. So a statistician wishes to estimate with 95% confidence, and it's important to note that actually that margin of error formula only works with 95% confidence. Now, we never really see anything except 95% confidence or 5% significance, which means the same thing. So I wouldn't panic about that, but often we see this 95% confidence thrown in, and the reason is it's to make it mathematically correct. The statistician wishes to estimate with 95% confidence the proportion of students who live within a certain distance of school. She wishes to be accurate within 10 percentage points. What that actually means is 10%. So she wants the margin of error to be less than or equal to. So she wants the margin of error to be less than or equal to 10%. That's basically what it's saying. So we get 1 over the square root of n to be less than or equal to 0.01. Let's multiply both sides by root n, which is definitely positive, less than or equal to 0.01 times root n, and divide by 0.01, less than or equal to root n. I wouldn't use the reciprocals here because if you use the reciprocals you have to be really careful about the inequality. We're going to square both sides. When you square both sides, we're left with 100 less than or equal to n. So therefore minimum sample size, the smallest we can probably have, is 100. N equals 100. So nice little questions, they tend to throw those in at the end. Just make sure you know your margin of error formula. Example 6.2, hypothesis testing with the mean. So there are two types of hypothesis testing that you need to be able to do. The first one is the mean and the second one is the proportion. So keep an eye out. Sometimes students just learn off a formula and throw it in wherever. But a survey of 100 shoppers, so that's telling us that there's a sample, was randomly selected from a large number of Saturday supermarket shoppers. That is definitely a sample. It showed that the mean was this. Now, that is the mean of the sample. So they have worked out the mean of this sample of shoppers. So when we talk about mean of a sample, we're talking about X bar. The standard deviation was 20.73. Find with 95% confidence. So again, that's just making it mathematically correct. We can only work with 95% confidence. Find confidence interval of the mean. So confidence interval of the mean. So you could be asked to do the confidence interval of the proportion. So you just need to keep an eye on what you're being asked. There is a formula that people learn off for the confidence interval of the mean, but we're going to actually work it through and create this formula together using this formula from your log tables. So to create the confidence interval, we're going to use this little formula from page 34, but you need to know how to create it. So we say that the actual mean is going to be somewhere between X bar, which is the sample mean, plus or minus 1.96, because we're dealing with 95% confidence, that's the z-score. And then we have the standard error of the mean, sigma over root n. How that actually looks is X bar minus 1.96, standard deviation over root n, is less than or equal to mu, is less than or equal to X bar plus 1.96, standard deviation over root n. Subbing in what we have 90.45 minus 1.96 times 20.73 over, that can all go over square root of 100, less than or equal to mu, less than or equal to 90.45 plus 1.96 times 20.73 all over square root of 100. And when we work that out, we get correct to two decimal places because it is money 86.39 is less than or equal to mu, less than or equal to 94.51. So basically the best thing to do is to try and remember this rather than learn it off, because if you learn it off, chances are you'll learn it off wrong. So the actual mean is going to be the sample mean plus or minus some correction, because the sample mean is just an estimation, so we want to try and make it more and more correct. How we do that is we multiply by the standard error of the mean, but we multiply by 1.96 times that because we're talking about 95% confidence. So the supermarket has claimed that the mean amount spent by shoppers is 94. So there's no mention of any kind of sample here, so that is mu equals 94. Based on a survey, test the supermarket's claim in the 5% level of significance, which is another way to say 95% level of confidence, and clearly state your null hypothesis, alternative hypothesis, and your conclusion. So students really struggle with this, but actually it's very, very simple. If you're doing a hypothesis test for the mean, the null hypothesis is always mu equals, and the alternative hypothesis is mu does not equal, and then we've covered everything. So you can put this then in words. The mean amount spent by shoppers is €94, and the alternative is the mean amount spent by shoppers is not 94. Is not 94. And that covers everything. It's either 94 or it's not 94. Put these out. So you will get your marks for just leaving it in mu equals and mu does not equal, but it's helpful for you to have it in terms of 94 and not 94. So you can use the confidence interval from above. However, I'm going to show you a second method where we can use for these. So there's three methods. You can use your confidence interval, you can use z-scores, or you can use p-values. It usually falls between one of the first two because p-values, you generally will only do them if you're specifically asked to do them. The rule of thumb for me would be if I do the confidence interval, I'd use the confidence interval. I do just want to show you the second method for z-scores. So on page 35, you have a formula, and that formula is z is equal to x bar minus mu all over sigma over root n, and that's helping you to compare your x bar and your mu. So that's called a one sample z test. It's under the hypothesis testing in the log tables. So we're going to work with that. So z is equal to, we have x bar from the last one, 90.45, minus mu, which is 94, all over sigma, which doesn't change, it's a standard deviation, 20.73, all over square root of 100. When you work out that z-score, I always do it to two decimal places because that's all that's in the log tables, and we get minus 1.71. For 95% confidence, our z-score is going to be between minus 1.96 and plus 1.96. So does our z-score sit in there? Yeah, it does. So what that's telling us is it's sitting in the area that we want it to sit, so we will accept. So what we have is, since 1.96, our z-score is less than or equal to minus 1.71, less than or equal to 1.96. So since that's true, and our wording is important here, fail to reject. So we're not 100%, we're not going in fully going, yeah, we accept. We're just going to say, well, we fail to reject the null hypothesis. And that is our result. You do also need then a conclusion, and our conclusion will be, therefore, based on the above, the supermarket's claim seems to be correct. And that's linking it back to the question. The supermarket's claim seems to be correct. So a good idea to do at the start is actually to make a note of which one is the claim. So for us, the null hypothesis is the claim, but sometimes the alternative hypothesis is the claim. So be careful in those cases, because you seem like you're contradicting yourself, and when you'll say we're rejecting the null hypothesis, and then the next one you're saying, well, their claim is correct. So just do anything you can to make your life easier and make sure that you can quickly identify what the claim is versus what the actual null hypothesis is. The null hypothesis will always be mu equals, and the reason for that is because we have to do a mathematical calculation, and that mathematical calculation can't be right sometimes when it's mu equals and sometimes when it's mu not equals. We have to follow a very strict guideline. So for the maths, the null hypothesis will always be mu equals. The third part of this question is, find the p-values of the test you performed in part B above and explain what this value represents in the context of the question. So this is, I suppose if you read through the question and you see p-values coming up, having the z-scores done will make your life easier. If we had just used the confidence interval in part B, we would still have to go and calculate the z-scores here. So what p-values are, is they're asking another way, should we accept or reject that null hypothesis. So to calculate, and again, this is not in the log tables. So it's not in the log tables. You need to be able to work that out. So we're going to have twice the probability that Z is less than this negative number, but it might be greater than the positive number. Effectively what we're going to do, we're going to look at the tails. We want to figure out this tail, where this is minus 1.71, and also this tail, which is plus 171. Because this is symmetrical, simply doing it once is absolutely fine. And that is 2 times 1 minus probability that Z is less than 1.71, which is 2 times 1 minus 0.9564, which works out as 0.0872, which is 8.72%. And this p-value is looking at what's the probability of ending up in the extremities. What's the probability that we're wrong? And the probability we're wrong is 8.72. Now we're looking at this at a 5% level of significance. And when we talk about 5% level of significance, it's the chance we're wrong. So instead of a 5% chance we're wrong, we now have an 8.72% chance. So 5% level of significance, 5% chance we're wrong. So I'm going to try put this 5% here. So there's my 2.5 and my 2.5. So they're the red parts. They're the parts where we're in rejection. But look where those blue parts are. Those blue parts are in the main part of the graph where we would accept it. So because 8.72% is greater than 5%, so because it's in the main body of that 95%, we fail to reject. Or to reject H0, which is the null hypothesis. So what does this actually mean in the context of the question? So this means that there is more than a 5% chance that we do not reject the null hypothesis. I think with p-values it can be quite hard and quite difficult to understand it if you think of it in terms of our actual diagram and the extremities. If our p-value was out in those extremities, that means, okay, we're in the rejection piece of our graph. If it's in the body, like it is here, we are in the accepting or the fail to reject zone. Example 6.3, working with the proportion. So this is from a section B question 2018, and it has a little bit of calculus in it, which we don't usually expect to see on paper 2. But this is just another example of you need to be aware that they can ask anything anywhere. So the paper 1, paper 2 is just really a guide more than anything. So part I here, put a tick in the table for each statement to indicate whether this statement is always true, sometimes true, or never true. In the table, n stands for sample size and p hat is the sample proportion. When forming confidence intervals for a fixed n and a fixed p hat, an increased confidence level implies a wider interval. So an increased confidence level, so the more confident you are, implies a wider interval, and that is true. And what they're basically saying is, if you want to be more accurate, you're going to have to say, well, there's more possible answers. And that is one of the big questions when we talk about inferential statistics. It's where does it start becoming silly? Where do we actually get no real benefit? So there's a 99% chance that the temperature today will be between 0 degrees and 20 degrees. Like, that's of no benefit to us. You want something that is as accurate as possible, also that will give us give us enough actual information that we can work with. As the value of p hat increases for a fixed n, the estimated standard error of the population proportion increases. Now, that is only sometimes true. And the reason that is only sometimes true is if we take a look at page 34, that this they're talking about is p hat. So what we use in our formula is p hat bracket 1 minus p hat. And the reason this only sometimes is true is because we're multiplying this p hat by 1 minus p hat. So as one goes up, the other one effectively goes down. So that sometimes will be true and sometimes will be false depending. And we're going to do a little bit of work on that top line to really understand that in the next part of the question. So as the value of p hat bracket 1 minus p hat increases for a fixed n, the estimated standard error of the proportion increases. So as that top line increases, the standard error of the proportion increases. So this whole thing increases. And yeah, that is true. That will always be true. As that top line gets bigger, this whole fraction gets bigger. As n, the number of people sampled increases for a fixed p hat, the estimated standard error of the population proportion increases. No. If this n, so let's go back here for a sec. If this n gets bigger, then the fraction gets smaller. So the actual standard error of the proportion will decrease. So that's never true. So we're focusing on this piece here. And we're going to work with that a little bit more. So that's on the bottom of page 34. And that is used when we're working with the proportion. So using calculus or otherwise, find the maximum value of p hat bracket 1 minus p hat. The or otherwise you could actually use completing the square. So I'm going to call this just m. So it looks a bit mu-ish. I just want a letter m just to help me. And when we do this, we're going to multiply it out just to make life a little bit easier. P hat minus p hat squared. So I'm going to differentiate this with respect to p hat, and I'm left with 1 minus 2p hat. To get the maximum value, I let the first derivative equals 0, so I get 1 minus 2p hat equals 0, so that means minus 2p hat equals minus 1, therefore p hat equals a half. So that's the value of p hat that will give a maximum value of our m. Therefore m max is going to be a half bracket 1 minus a half, which is a half by a half, which is a quarter. So maximum value we can get there is a quarter. Hence find the largest possible value of the radius. Now this word threw a lot of students. The radius of a 95% confidence interval for the proportion. So what I'm going to do is I'm going to actually set up the proportion. So the proportion is going to be p hat plus or minus, this side is plus, 1.96 times the standard error of the proportion. So very similar to what we've seen for the mean. So we get p hat 1 minus p hat all over n, and this is p hat minus 1.96 standard deviation, or sorry, square root of p hat 1 minus p hat all over n. So that is the confidence interval. So this is the confidence interval for the population proportion. Now, when we do this, there is a nice symmetry to it. And basically we're saying the actual population proportion is the sample population proportion plus or minus some like adjustment. And this adjustment here that we add and subtract is known as the radius. And think about that, like we're basically adding and subtracting it. It's going to be the same both sides. It's effectively the radius. If we think about that drawn out, here's our P. And we end up with P hat in the middle, and the P hat is going to have a plus the radius and then minus the radius to get to the edge of both of our confidence intervals. So when they talk about radius, that's what they're talking about. So we're trying to find the largest possible value, and the largest possible value of the radius will happen when that top line is maximized. So 1.96 square root of, we've already maximized that top line and figured out that it was a quarter over n, which is 800. They've told us the sample size is 800, and when you work with that, that works out as 0.03464. For proportion, I like to work in percentage, so that's 3.46%. So this line here, we've just maximized it up here, so that's a quarter. Because remember, we figured out the P hat that would give us the maximum value, and so on. Example 6.4, hypothesis testing with the proportion. A motoring magazine collected data on cars on a particular stretch of road. Certain details on 800 cars were recorded. So they've straight away told us, maybe not explicitly, but that we're dealing with a sample where n is 80. The ages of the 800 cars were recorded. 174 of them were new, so that means less than a year old. Find the 95% confidence interval for the proportion of new cars on the road. Give your answer to 4 significant figures. So we're going to use the standard error of the proportion. So if I want to figure out the proportion, I'm going to use the fact that the P hat, so the sample proportion, plus or minus 1.96 times this standard error of the proportion. So we have P hat, so slight difference to what's in the tables. We use P hat because that's what we have, over n. So we need to figure out, well, what is P hat? So we know 174 of the cars are new, but we want that out of 800. We want it as a proportion. So we're going to leave that as a fraction, and we end up with P hat minus 1.96 standard deviation, or sorry, square root of 1 minus P hat over n, less than or equal to P, less than or equal to P hat plus 1.96. So sometimes breaking this down into just a plus and minus, students are going, okay, I see, I don't have actually this huge formula to learn off. So we get 174 over 800 minus 1.96. Now, square root, we have 174 over 800 times 1 minus 174 over 800 all over 800 less than or equal to P less than or equal to 174 over 800 plus 1.96. Square root of 174 over 800, 1 minus 174 over 800, all over 800. So just a little trick here, if you put one side of that into the calculator, you can go back and simply change the plus to a minus, and when you do that, you're going to figure out very quickly, oh, the second answer without having to retype everything. So when you put that into the calculator, we 1889 less than or equal to P less than or equal to 0.2461. So that's 18.89 is less than or equal to P. It's less than or equal to 24.61. I like my P's in percentages. You do not have to use percentages. All you need to make sure is that you have 4 significant figures. The data on the speeds of these 800 vehicles is normally distributed with an average speed of this. So that is the average of their speeds. It has a standard deviation of 12. And what proportion of cars on this stretch of road would you expect to travel at 95 kilometers per hour? Now, we're not doing a hypothesis test here, so we're going to use our normal standardizing formula. That means we're going to take our mu, our mean, as 87.3. Now you might say, oh, but hang on, it's a sample. Yeah, it is, but for the purpose of this part of the question, we're taking that as these are normally distributed. It is absolutely fine to use the standardizing formula once they're normally distributed. Usually with the sample, we don't know if it's normally distributed or not. We're comparing it to the actual full population. Here, all we worry about is we know that these speeds are normally distributed, which means we can use this as mu. It wouldn't be right to use a hypothesis test here because it's nothing about hypothesis. Kilometers per hour, because it's not a hypothesis test. They want what proportion of the cars in this stretch of road would you expect to be traveling over 95 kilometers per hour. Proportion is another way to say probability. So what is the probability that X is greater than or equal to 95 kilometers per hour? That's effectively, well, actually they've just said over, so it's better to write it as greater than. First thing we're going to do is we're going to say, well, then X is 95. Use this formula to find the z-score to standardize it. 95 minus 87.3 all over 12. And when you work that out to 2 decimal places, because that's all the log tables have, we get the probability that z is actually greater than 0.64. So now we're going to work that out. I can't actually work that in the calculator, or in the log table. So we're going to do 1 minus p is z is less than or equal to 0.64. And that is 1 minus, looking that up in the log tables, we get 7389. And that gives us 0.2611, which is 26.11%. So when you see proportion, it can also mean percentage or probability. So proportion in itself, if we talk about sample proportion, if we talk about proportion of the population, they're very specific. But here where it just said what proportion, that's another way to say the probability. So that's another way to say probability. Okay. So part 3. The driver of a car was told that 70% of speeds recorded were higher than his speed. Find the speed at which the driver was recorded. Give your answer correct to the nearest whole number. This kind of question can cause a lot of problems and students just don't even know where to start. My suggestion on a lot of this is to actually just sketch it out. So here's our normal distribution, and 70% of all the speeds are recorded higher than his. So it's symmetrical, half is to the right of this midline. So I'm going to say maybe in around here, to the right of this, that is 70% of speeds were higher. So he must be in around here. Because of where he is, I'm going to call this a negative z. So 70% is to the right of him. Now, if you go to your log tables on page 36, this diagram does not look at like the diagram at the top. We can only work to the left. So we're going to use the idea that this is symmetrical to basically instead flip this and say, well, if I took 70% to the left of a z-score, it would be the positive version of that z. So now we need to look that up in the tables. So here's my little table here, and we're trying to find something as close as possible to 70%. The body of the table, that's going to be 0.7. So is there a 0.7? No, but we're going to be somewhere in between these two. So we're going to actually choose this one here because it's closer. It's 0.0015 close to 0.5. Try again. It is 0.0015 to get to 0.7, while the other one is 0.0019 over. So just be careful. Sometimes the one lower is actually closer. So that's our answer. So we have our z here is 0.52. That means the negative z is minus 0.52. So working with our formula, which we had before, so z is equal to x minus mu over sigma, and that gives us minus 0.52 is x, that's what we're looking for, minus 87.3 over 12. We have minus 0.52 by 12 equals x minus 87.3. X is equal to, that works out as 6.24, so minus 6.24 plus 87.3, and when we get that, so 87.3, we get 81.06, and they wanted that correct to the nearest whole number, so that means x is 81 kilometers per hour. A road safety program was carried out in the area using posters, signs and radio slots. After the program, the motoring magazine recorded the speeds of 100 passing cars. So this is another sample N. The magazine carried out a hypothesis test at the 5% level of significance and determined that the average speed had changed. Okay, so now when we talk about hypothesis test, we're talking about mu equals, and mu does not equal. Let me clean up my mu there. So this is speed has not changed, and the alternative hypothesis is the speed has changed. And the p-value of the test is 0.024. So our p-value equals 0.024. Again, I like to work in percentages. That's 2.4%. What can the magazine conclude based on this p-value? Well, because that p-value is smaller than 5%, so that means if we were to draw that out, okay, so if we were to draw that out, and there's my 2.5 and my 2.5, so there are my two ends. 2.4 is like these little pieces here. So actually these are in the tails. So that means that we're in the rejection area. So we would reject, or we would fail to accept. So we would fail to accept H0. So I forgot to put in my H0, and that's H1. So fail to accept H0. So that would mean that the speeds have changed. So they've asked us for two parts to this. The conclusion is, so what can the magazine conclude? So speeds have changed, and we have our backup here, so we fail to reject, or we fail to accept, i.e. we reject the null hypothesis. The magazine found the average speeds for this sample was lower than the previous established average speeds of 87.3. Find the average speeds of the car in this sample. Okay, so we did a p-value, and to go back to the p-value, we basically had, and I'm going to just do a little bit of a sketch here. So we had one, oh, that's very bad. Usually I bring these in because I'm so bad at drawing them with this pen. Now, so roughly there we go. So we're saying that we have about 2.4%. So that means in each piece here, that's about 0.012, and that's proportion 0.012. So if we were to actually delve a little bit deeper into that, I'm just going to take the right hand side because it's always easier to work the right hand side. If this was 0.012, then to the left of that, it's going to be 1 minus 0.012. And that would leave us with 0.988. So that would be the proportion that is to the left. So if we go to our tables and look for 0.988, that works out as about 2.26. So our Z score here is about 2.26. Now, the magazine found that the average speed of this sample was lower, so we're actually going to be working with the negative. So we're going to say, well, Z was actually minus 2.26 because we were told it was lower. It's always easier to work with the upper one when we're working in our tables. We're dealing with it being lower. How we worked out this Z was using our hypothesis test formula, which was x bar minus mu or sigma over root n. And working with that, we get minus 2.26 is equal to, we don't know what this x bar is, minus 87.3 all over sigma square root of 100, and we want to work that through. Okay, so I've just tidied that up a little bit so we can work with it. So we're going to multiply both sides by 12 over root 100, so we get minus 2.26 by 12 over the square root of 100 is equal to x bar minus 87.3. That gives us x bar is equal to minus 2.26. I'm going to just stick it all in the calculator at the end. You can fill it in as you go if you prefer. Plus 87.3. And when you put that into the calculator, we get 84.588. And they want it correct to one decimal place. So we get 84.6 kilometers per hour.